Hello everyone. This is our session 4. With this question session 4 will include our top chapters, chapter number 6 and chapter number 7. Chapter number 6 is second law of thermodynamics, and chapter number 7 is entropy. Okay, so we will do the questions, solve the questions for both the chapters in this session. Okay, now before starting the session, there are few questions from the application of first law, uh, from question session 3, which I didn't complete in that session, so I will solve it here first. So we were doing this question: the heat capacity of a constant pressure of a certain system is function of temperature only, and is expressed by Cp is equal to the given expression. And it is mentioned that the system is heated while it maintained at a constant pressure, okay, of 1 atmosphere, and its volume increases from 2000 centimeter cube to 2400 centimeter cube, okay, and temperature increases from 0 to 100 degrees Celsius. We have to calculate the magnitude of heat interaction. And second, how much does the internal energy of the system increases, okay. Now first, we have in first part we have applied Q is equal to Cp delta T, and we have integrated from 0 degree Celsius to 100 degrees centigrade. So we calculated the value of heat interaction to be this, okay. Now for B part, it is asked that how much the internal energy of the system increases, okay. So here we can apply first law of thermodynamics first. So first law indicates that Q is equal to delta U plus W. So we know the value of Q from the part A. Delta U value you have to calculate, and work done value we can calculate it by work done is equal to P into delta V. And why this? Because it is mentioned that it is at a constant pressure of 1 atmosphere, okay. Now we will apply 1 atmosphere is equal to 101.325 kilopascal, okay, into delta V is equal to 400 centimeter cube. 400 centimeter cube can be written as 10 to the minus 6 meter cube, okay. So this term will be in kilojoule, okay. Now let me calculate the value. Okay, so we get here 40.53 joules, okay. So we can multiply it by 10 power 3 to get the value in joules, okay. So we get 40.53 joules. Now we can calculate delta U value for using this expression as Q, that is 238.32 minus 40.53. Let me solve this first. 238.32 minus 40.53. So we get delta U to be 197.79 joule per kg, okay. And obviously this was also in per kg, okay. No, actually it's not in per kg, because the unit of Cp is in joules per degree centigrade. So this Cp should be mass heat capacity, okay, not specific heat capacity. It is total heat capacity, okay. Next we will be moving to question number 36. So it mentioned that an insulated storage tank that is initially evacuated is connected to a supply line carrying a fluid at specific internal energy U, specific enthalpy H1. So it is mentioned that a rigid box, let's say this is a system, this is our storage tank, our is insulated storage tank, okay. Insulated storage tank here, okay. Now it is mentioned here that the insulated storage tank initially evacuated. It means that m1 is equal to 0. There is no initial mass in the system, and supply line carries a fluid at a specific internal energy ui, enthalpy hi. The valve is opened, and so there is a valve, and valve is open and fluid is allowed to enter. Fluid flows into the tank from supply line and reaches the pressure equal same as the supply line. Okay, so if here what is the pressure P, then here again it reaches the pressure P. So the final specific internal energy of the fluid in the tank is equal to, so we have to prove that U2 is equal to HI. Okay, so let's assume that system goes from state 1 to state 2 during this process. Okay, so first we will apply the conservation of mass. From conservation of mass we can write it as m2 minus m1 is equal to mi minus me. Okay, so here we know that m1 is 0. Okay, now there is no mass exit from the system, so this me also is 0. So from here we get mi is equal to m2. Okay, now if we apply the energy equation, we get u2 minus u1 hi mi, or we can write that total energy instead. We can write it as m2 u2 minus m1 u1. Okay, is equal to hi mi plus q dot minus he me minus w. Okay, not q dot here because we are talking about total amount of heat. Okay, so this is the equation for energy conservation. Now we can like this m1 is 0, so this term will be 0. Here we also know that there is no mass exit, so this term will also be 0. There is no heat transfer, this term will be 0. There is no work transfer, so this term will also be 0. From here we get m2 u2 is equal to hi mi, and from this expression we also know that mi is equal to m2, so we can obsolete both terms, and from here we get h2 is equal to hi. So this is what we have been asked to prove, okay, in this question, and we have already proven that. Now for if we consider that the fluid is ideal gas, we can do some further calculations. So we can write u2 as cv t2 is equal to hi as cp ti. From here we can get t2 is equal to cp by cv times of ti, that will be gamma times of ti. So here we can see that in case of we are filling an evacuated tank, so the final temperature in the tank will be gamma times of the inlet temperature of the fluid, okay, of air, if we are taking ideal gas into consideration. Okay, ideal gas. Now with this question we have completed our last question I intend to solve with you on the topic application of first law of thermodynamics. Okay, so from here we will start our chapter 6 question related to chapter 6, that is second law of thermodynamics, and chapter 7 entropy. Okay, so we will start with this question 1. So it is mentioned that a cyclic device operates between three thermal reservoir temperatures. Three temperatures are shown here. So let's say this is T1, this is T2, and this is T3. Okay, now the heat is transferred from a cyclic device. It is assumed that the heat transfer between each thermal reservoir and classic device and cyclic device takes place across negligible temperature difference. Interaction between the cyclic device and the respective thermal reservoir are shown in the figures. Cyclic device can be reversible heat engine, the reversible heat pump, or a refrigerator. A irreversible heat engine, an irreversible heat pump, or an irreversible refrigerator. Okay, so first of all we have to calculate what should be the change. So in first what we should do is we should check whether Clausius inequality is satisfied or not. Okay, so what is Clausius inequality? Clausius inequality is for every possible device, if it is working, then cyclic integration of del q by t must be less than equal to 0. Okay, so we will apply it in here also. So we know that let's say that let's consider the first as a system first. So from here we get the 100 kilojoule work is getting out of the system at 1000 Kelvin, minus 50 kilojoule of work is getting out at 500 Kelvin, plus 60 kilojoule is work supplied at 300 Kelvin. Okay, so we will find these values. This is okay, 300. Okay, so what is this? This is cyclic integration of del q by t, and this value is equal to let's calculate the value. So this will be equal to so we get value is equal to 0. Okay, so from here we can say that for this particular system, its cyclic integration of del q by t is equal to 0. It means that system is reversible. Okay, so since we need know that the system is reversible, so it can either be a heat engine or a heat pump or a refrigerator. Okay, so to calculate that, we should first check that whether the system is heat work producing or work absorbing device. Okay, so we should calculate q net here, sorry, w net here. So w net will be like heat supplied to the system, that will be, let's say this is q1, this is q2, and this is q3. So q1 plus q2, that is supplied, minus heat withdrawn or heat subtracted from the system. Okay, so here for this case, this cyclic device will be our system. Okay, so we get 100 plus 50 minus 60 is equal to 90 kilojoule. So this is the work done, work produced by the cycle. So this cycle should be a reversible heat engine. Okay, so option A is correct. Okay, now moving to next question, we see that a reversible engine operates between temperature 1000 Kelvin and 400 Kelvin. The engine drives the refrigerator, which operates between between T2 is equal to 400 Kelvin and T3 is equal to 200 Kelvin. Okay, so what it is telling us that a reversible heat engine operates between temperature of, let's see. Okay, so this is question number 2. You are starting from here. Okay, so 1000 Kelvin, T1 is equal to 1000 Kelvin, and it is connected to a heat exchanger. Sorry, heat engine. A reversible engine operates between temperature of T1 is equal to this to T2 is equal to 400 Kelvin. Okay, now the work done produced by it, okay, is used. The engine drives a refrigerator which operates between temperature T2 and temperature T3. Okay, let's say this is a temperature T3 is equal to 200 Kelvin, and it is said that this is our refrigerator. Okay, the energy transfer to the engine is okay, so this is given as q1 is equal to 2000 kilojoule. Okay, now it is a refrigeration working between the temperature limits, and the net work output of the combined engine and refrigeration cycle is 300 kilojoule. Okay, after this system, also after this setup, we are able to obtain additional work done of 300 kilojoule. Okay, the energy transfer to the refrigerant is. Okay, so how much energy transfer to the refrigerant. So this energy, this heat, let's say it q let's say that q2 is released here, this let's say it is q3, and q4 is released here. Okay, so we have been asked what will the value of q3, okay, the energy transfer to the refrigerant. Okay, for this we can proceed as, let's see, from here we can see that since the engine is reversible, so del q by del t for this engine must be 0. So 2000 minus 2000 divided by 1000 plus q2 divided by 400 must be equal to 0. So for this we can get q2 is equal to 800 kilojoule. Okay, and since q2 is equal to 800 kilojoule, we can calculate that the work produced by the heat engine, okay, will be equal to 1200 kilojoule. 2000 kilojoule minus q2, that is 800, will be 200 kilojoule, and from this 1200 kilojoule we can still obtain 300 kilojoule of work. So it means that let's say this w1, okay, so w1, and we can still supply w2 heat, work to the refrigerant or refrigeration cycle, which will be equal to 1200 minus 300 is equal to 900 kilojoule. Okay, next what we can do here, we can like if you have to calculate q3, we know that since it is mentioned that since the reversible engine operates between temperature and the energy drives the refrigerator. Okay, let's assume here that our refrigeration system is also a what reversible cycle. Okay, so our q4 value will be equal to, in any case q4 will be equal to q3 plus w2. Okay, now if we like apply process inequality for reversible system here also, so here we can get q3 plus w2 upon 200 minus, so this heat q3 is rejected from here, minus q3 by 400, okay, is equal to 0. So from here we can get 400 q3 plus 400 w2 is equal to 200 q3. So from here we can calculate q3 is equal to minus 2 times of w2, which will be equal to, sorry for the misconception here. So for refrigeration the required temperature is lower temperature, so I made some mistake here, let me correct it first. Great. Okay, so here the heat will be rejected from 200 Kelvin thermal reservoir. Let's say this to be q3, and here it will be q4, which will be further be equal to q3 is equal to q3 plus w2, and we can correct this one also. Okay, so this term will be negative, this term will be positive, and upon 400 minus q3 will be negative upon 200 equal to 0. Okay, now from here we can calculate 200 times of q3 plus 200 times of w2 is equal to 400 times of q3. So we can calculate q3 is equal to w2, which will be equal to 900 kilojoule. Okay, so answer is C. Next we will be moving to our question number 3. It is given that a heat engine operates between three reservoirs, R1, R2, R3, for every cycle the engine accepts 10 kilojoule from R1 and rejects 60 kilojoule to R2 and 30 kilojoule to R3. Let me draw the figure first. So let's say that this is our engine. Okay, now it is in interaction with three reservoirs. Let's say this is reservoir A, this is okay. Okay, so let me draw the figures here. So let's say this is reservoir R1 at temperature 550 Kelvin. This is R2 at 450 Kelvin. This is R3 at 350 Kelvin. 350 Kelvin. Okay. Now for every cycle the engine accepts heats of 100 kilojoule from R1. So it is mentioned that this heat is transferred to the engine at 100 kilojoule. Okay, and rejects 60 kilojoule to R2. 60 kilojoule to R2 and also rejects 30 kilojoule to R3. Okay, so the value is 30. Okay, now it is asked the engine efficiency. What will be the engine efficiency? So if the engine is operating between these three reservoirs, there is certainly some work done, work output. So let's calculate the work output first. Okay, so this work output will be equal to net heat. Okay, so heat received by the system by the engine, that is 100 kilojoule, minus heat rejected, that is 60, minus 30 is equal to 10 kilojoule. Okay, and the heat supplied, so efficiency is we have seen that desired effect, that is work done upon heat supplied, that is Q1, and this will be the Q1 because this heat is supplied to the system. The both 60 kilojoule and 30 kilojoule is rejected by the engine. Okay, so from here we can calculate the efficiency is 10 upon 100, that will be 0.1. Okay, and option is A. Next we will be discussing question number 4. So for question number 4, it is mentioned that Carnot engine C1 operates between temperature limit of 100,000 Kelvin and 900 Kelvin. The second Carnot cycle C2 operates between temperature limit of 400 and 450 Kelvin. Both engines produces same amount of work. Which one of the following statements is true regarding the efficiency and heat rejection of 1 and 2? Okay. So while we talk about this, let's first, before this we should calculate. Okay, since work done by both cycles, W1 is equal to W2, this is given. Okay, now we can calculate the efficiencies first. Okay, so efficiency of 1 is equal to from Carnot efficiency, we know that earlier we studied that efficiency, Carnot efficiency can be written as 1 minus TL by TH. Okay, so we will use this same equation. So efficiency 1 is equal to 1 minus TL is 900 divided by 1000, so this will be 0.1. Okay, now efficiency 2 will be 1 minus TL is 450 divided by 500. Okay, so this will come out to be again 0.1. Okay, 5 9s are 45. Okay, so this will be same. So from here we can see that eta 1 is equal to eta 2. Now this eta is represented by work done by Q supplied. Okay, QS. Okay, now since for both equations efficiency is same, okay, and work done same, so QS is also Q supplied to 1 is equal to Q supplied to 2, and since Q supplied is same, so Q rejection should also be same. Okay, so our correct answer is D. Now we will be moving to question number 5. So the question number 5 is mentioned to a match list question. So the zeroth law of thermodynamics is also called thermal equilibrium. Okay, first law of thermodynamics is called conservation of energy, and second law of thermodynamics is called is magnetic equilibrium, conservation of energy, thermal equilibrium, thermodynamic temperature scale. 3. Okay, so 213 is the correct option, D. Okay. Now moving to next question number 6. Which of the following statement is violation of second law of thermodynamics? Okay, so we will see equation one by one. So first equation, it is so question number 6. For question number 6, we will be seeing the first equation. It is impossible to construct a cyclic operating device which absorbs heat from a single thermal reservoir and produces an equivalent amount of work. Okay, so this is the second. Okay, so it is saying that it is a cyclic device which is absorbing heat from single reservoir and producing equivalent amount of work. So Q is equal to W. So which law? So you should remember. So this device is also called as perpetual motion machine of second kind. Okay, so is correct. Is a violation of second law? No, it is not a violation of second law. Okay, next we will see question number, sorry, part 2. It is possible to construct a device that absorbs heat from a low temperature body and direct it to high temperature body without an external work. So this is our closest statement. Okay, so closest stated as that this type of engine, this type of device is not possible. Okay, so and since it is mentioned at high temperature without any external work, so this is a violation. Okay, violation of second law of thermodynamics. Okay, next. Okay, sorry for 1 minute. It is mentioned it is impossible to construct a cylindrically operated device. So this is follows the second law. So okay, that is correct. It is not a violation. Okay, and here it is mentioned it is possible. Okay, so this is a violation of second law. Next, in third part, it is mentioned that a reversible heat engine has a higher efficiency than an irreversible heat engine between same temperature limit at a constant temperature. A reversible heat engine has a higher efficiency than an irreversible engine. Okay, this also is correct. So it is not a violation of second law of thermodynamics. Okay, so only option 2 is the answer is B. Okay, next two reversibly engines E1 and E2 react heat to a common reservoir at temperature T, and engine E1 receives a heat from T1 and reverse for W1. The engine E2 operates same amount of heat from reservoir at temperature T2 and reverse the work to W2. Okay, so it is mentioned that two engines E1 and E2 are receiving heat from two different reservoirs. Okay, E1 E2, and here this is like temperature T. Okay, so this engine supplied in W1, this is supplying heat W2, work W2, and since it is mentioned that both are reversible engine, so and here it is mentioned that T2 is, okay, let me write it another pen. So it is mentioned that T2 is less than T1. So since T2 is less than T1, we can say that so efficiency formula, we can see efficiency of a reversible engine. It is 1 minus T by TL by TH. Okay, so here if we see for engine E1, so our efficiency 1 is equal to 1 minus T by T1, and efficiency 2 is equal to 1 minus T by T2. Now let's say that T2 is less than T1. If T1 value is small, then efficiency will be larger. So we can say from here that efficiency of 2 is greater than efficiency of 1. Okay, and efficiency is also rated as in terms of W and heat supplied. Okay, now if we talk about here, let's say it is also mentioned that both receives heat from a common reservoir temperature E2. The intern E1 receives the heat from reservoir, the engine E2 receives same amount of heat. Okay, it is mentioned that they both receive same amount of heat. So let's say this is Q, so this is also Q. So efficiency will be W2 by Q is greater than W1 by Q. So from here we can get W2 is greater than W1. Okay, so our correct option is C. Next we will be moving to question number 8. In question number 8, it is mentioned that inventor claims that a heat engine has following specification. Okay, the power developed, fuel burnt, CV, temperature limit, cost of the fuel, value of the power. Okay, so first we have to see that if the like it is asked to performance of the engine is possible, not possible, most economical, uneconomical. So since we know the temperature limit at which between which it will be working, that is 627 degrees Celsius and 27 degrees Celsius, which will be converted to TH is equal to 627 plus 273, so it will be 900 Kelvin. Okay, now TL will be 300 Kelvin. Okay, so the efficiency, Carnot efficiency, that will be maximum possible efficiency of the system. This system for a reversible cycle will be 1 minus TL by TH, 300 by 900, that will be 2 by 3 is equal to 0.667. Okay, now for the given system, the efficiency actual, if we calculate, so the actual efficiency is calculated. How can we calculate actual efficiency? Actual efficiency calculated by work done upon heat supplied. Okay, so it is mentioned that power developed is 50 kilowatt. Okay, and the heat supplied is at rate of m. Since fuel is 1, so we can write Q is equal to mc delta T. Okay, so fuel burnt per hour is 3 kilojoule per hour, so we can convert it into per second. M, and then CV of fuel is given as 75,000 into, and then we know that the change in temperature. So for change in temperature we can take okay, sorry, so this is a burning of fuel. So we see that we are provided with mass, flow rate, and our CV value is given. So if it is CV, so it is mass into CV. Okay, this is not specific, this is CVU, the caloric value. So for that we don't require delta T value. Okay, so from here we can calculate the eta efficiency, actual efficiency value. Let me calculate it. So we get efficiency is equal to 0.8. So from here we can see that the actual efficiency which we receive in the cycle is greater than that of the maximum possible efficiency, or which generally happen in case of reversible engine. So from here we can say that this device is not possible. Okay, next we'll be moving to question number 9 and 10. So it is a direct question, link type question. So it is mentioned that two reversible heat engines working between three thermal reservoirs at temperature T1, T2, T3 respectively. Engine E1 received heat from reservoir at temperature T1 and rejected temperature T2. Engine E2 receives heat from reservoir T2 and reject to heat to reservoir T3. Okay, so it is given that there are three reservoirs, T1, second one is T2, and third one is T3. Okay, now it is mentioned that we have installed two engines between these points. Okay, engine E1, and here it is engine E2. Okay, now this engine E1 will, let's say, provide work done W1, this will provide work done W2. Okay, and let's say these are the amounts of heat that will be supplied. Okay, now it is mentioned that E2 receives heat from and rejects the heat. Okay, assume that the heat rejected by engine E1 is equal to heat input to engine E2. So from here we can write Q1 is the heat received from T1 to E1, Q2 is the heat rejected, and this Q2 heat will be received by engine E2. and next Q3 heat will be rejected to at T3. Okay. Now we are asked if the efficiency of the engine E1 and E2 are same. Okay, so if we are given ninth question that if eta 1 is equal to eta 2, then the reservoir temperature T2 can be expressed as. Okay, so we have to find the value of T2. What should be the value of T2? Okay, so since we have been provided with reversible heat engine, both are reversible, so we can directly use the relation of temperature here. Okay, so efficiency is equal to 1 minus TL by TH, that will be T1 by T1 here. Okay, and here it will be 1 minus T3 by T1. Okay, now we can directly oscillate 1. Now from here we get, okay, sorry, this should be T2. Okay, so we get T2 square is equal to T1 T3, and here from here T2 is equal to root of T1 T3. Okay, so option A is correct. Next we will move to question number 10. Question number 10, it is given that if work delivered by the engine E1 and E2 are same, the reservoir temperature T2 can be expressed as. So if it is given that if W1 is equal to W2. Okay, so if W1 is equal to W2, so we can say from here that okay, so we know that efficiency is equal to W by Q, so we can write it as W is equal to Q into efficiency. Okay, let me think a moment. Q supplied. Okay, this is Q supplied. Okay, okay, now let's see here first. We have been given so if W is equal to W2, so we can from here we can write Q1 minus Q2 is equal to Q2 minus Q3. So from here we can get Q2 is equal to Q1 plus Q3 by 2. Okay, and also we can write it as like if W is equal to QS into supplied into efficiency, so what else we can write? We can write efficiency in terms of temperature. Okay, so we can write W is equal to QS or we can like do it as, wait a minute, okay, or we can write it as okay, let's divide the whole equation by Q2. Okay, so we will get 2 is equal to Q1 by Q2 plus Q3 by Q2. Now from Kelvin scale, thermodynamic Kelvin scale, we know that Q1 by Q2 can be written as 2 is equal to T1 by T2 plus here it is can be written as T3 by T2, and so from here we can obtain it as T1 plus T3 by T2 is equal to 2, so we can obtain T2 is equal to T1 plus T3 by 2. So option B here is correct. Now moving to next question, we can continue question number 11. Here we have seen that one of the following pair of equation describes the irreversible heat engine. Okay, so we have to tell which one is the irreversible heat engine. So we know that for irreversible heat engine, our in closest inequality del Q by T must be less than 0. Okay, so we got two of these options, and we have to now tell for irreversible is our net Q is greater than 0 or less than 0. Okay, now we know that during irreversibility heat is definitely generated. Okay, now from first law we can see that integral of del Q is equal to W net. Okay, now since it is given that this is an engine, so W net must be greater than 0, so we can write integral of del Q must be greater than 0. So option A is correct. Okay, now moving to question number 12. We see that an inventor claims that his new concept engine, while working between temperature this and this, rejects 45% of the heat absorbed from the source. Okay, let's write the data. So it is given that TL is equal to 27 degrees Celsius will be equal to 300 Kelvin. We will directly at 273 273 value. Okay, and TH will be 327 plus 273 will be 600 Kelvin. Okay, so from here we can calculate the value of okay, leave it at. It is also meant that it rejects Q reaction will be 45% of heat supplied. Okay, now his engine is equivalent to which of the one of the following. Okay, so let's see here first. So ideal efficiency Carnot will be equal to 1 minus TL by TH. From here we can get TL by TH is equal to 0.5, so efficiency will be 0.5. Now since it is given QR is equal to 0.45 times of QS, we can get work done is equal to net work done is equal to QS minus QR. Now we can get it in terms of W net is equal to QS minus QR is equal to 0.45 QS, so this will be 0.55 QS. From here we can get W net by QS, which is itself is efficiency is equal to 0.55. So we can see here that this efficiency we have calculated is greater than Carnot efficiency. It means that this cycle that inverter claim is not impossible. So not possible. It is impossible. Okay, it is impossible. Moving to next question number 13. It is mentioned that three heat engines ABC operating on Carnot cycle use work substances argon, oxygen, and air respectively. Which engine will have higher efficiency? So we have studied that for Carnot cycle. Carnot cycle is a hypothetical cycle. Okay, hypothetical. And for Carnot cycle, the efficiency is only a function of both temperature limits T1 and T2. Okay, and it is independent of the type of working fluid. Okay, so here all of these will having the same efficiency. Okay, next question number 14. In a reversible heat engine operating in a cycle between the source temperature of 606 degrees Celsius and sink temperature of 20 degrees Celsius, the work done per kg heat supplied to the engine is. Okay, so we have been provided with TH is equal to 606 plus 273 is equal to 879 Kelvin. Okay, and TL is equal to 20 degrees Celsius, 20 plus 273 is equal to 293 Kelvin. Okay, now efficiency value of efficiency is given by 1 minus TL by TH is equal to 1 minus TL is 293 divided by TH is to 879. Okay, and we can be efficiency can be written as work done net upon heat supplied. Okay, so it is asked that work done per kg of heat supplied. Okay, so we have to calculate this value only. Okay, so we will calculate 1 minus 293 divided by 879. We get the value is equal to 0.667 kilojoule. Moving to next question, we move to question number 15. It is mentioned in question number 15 that a heat pump, so it is question of heat pump, absorbs 100 kilowatt of heat from. Okay, so let me draw a heat pump first. So this is let's say this is a heat pump. It is operating between two reservoirs, and it is mentioned that so let's say this is higher and this is TL, and it is given that heat pumps absorb 100 kilowatt heat from the outside environment, which is at 250 Kelvin. So it absorbs 10 kilowatt. Okay, of heat from environment, and while absorbing 15 kilowatt of work. so it is also absorbing work of 15 kilowatt, and it delivers the heat to the room, which must be kept warm at 300 Kelvin. Okay, the coefficient of performance of the heat engine, oh sorry, heat pump is okay. So what is the coefficient of performance? So okay, and this net heats that will be supplied to the room is, this heat will be work done plus this, so this will be 25 kilowatt. Okay, so we can say that COP of heat pump is equal to, COP of heat pump is equal to, we know that it is desired effect is here, it is 25 kilowatt, and the provided, what is provided is 15 kilowatt of okay. So we can calculate it by solving this. So how do you obtain the values? We can obtain by 5 to 25, 5 3s are, so COP is 5 by 3, which will be equal to 1.67. Okay, now some student might do like COP of the heat pump, they can like think this of as Carnot heat pump, and directly write the COP of heat pump is equal to TH upon TH minus TL, which will result in COP is equal to 6. Okay, but this is incorrect. Why? Because it is not mentioned here that the heat pump is reversible. Okay, this formula is only applicable in case of reversible. Okay, and here reversible word is not mentioned. And first and before that, even let's say in a question it is mentioned that the cycle is reversible, but if it is if the, when asking the coefficient of performance, and it is not mentioned that this is the like maximum possible COP, or reversible COP, or Carnot COP. Okay, and in question the heat supplied and work is given, so you must use this formula only. Okay, COP is equal to desired effect upon energy supplied. Okay, next, moving to question number 16, it is mentioned that the reversible heat engine operating between thermal reservoir 800 degrees Celsius and 30 drives a reversible refrigerator which operates between okay, so the heat engine is driving an refrigerator which operates between minus 15 degrees Celsius and 30 degrees Celsius. The heat supply to the engine is 19 kilojoule, then the net, and there is a net work output of 290 kilojoule. Okay, determine the cooling effect, heat transfer to 30 degrees Celsius thermal reservoir. So let's draw a like diagram for this this operation first. So heat engine operates between, let's say this is T1 is equal to 800 degrees Celsius will be 1073 Kelvin. Okay, 73 Kelvin. Okay, now let me think a bit. Okay, now this is operating this with this we are receiving a heat for an engine, and this engine is further reacting heat to another sink at temperature T2 is equal to 30 degrees Celsius, that will be 303 Kelvin. Okay, and next it is like also working with a refrigerator which is connected, which is also interacting heat with another source, that is at T3 is equal to minus 15 degrees Celsius will be 258 Kelvin. Okay, next it is mentioned that what is the cooling effect? Cooling effect will be heat like delivered from this air. Okay, here, so let's say this is this obtains amount Q1 which is given to be 1900 kilojoule. Okay, 1900 kilojoule. Okay, the net work output is given as 290. Okay, so let me ask you, what do you think this net work output here represent? So the net work output, it isn't mentioned that this is our work output of our engine. Okay, so this net work output will mean that it is the work output of engine and refrigerator combined. Okay, so this both system combined is delivering an work of, okay, and I might represent it in another way like I have done in previous question. Okay, Okay, so let's say that this engine is also supplying the work to the refrigerator. Okay, so let's say this is producing in W1 amount of heat work, and W2 amount of work is absorbed by refrigerator, and the remaining heat, which is called W net, is supplied outside the system, which is equal to 290 kilojoule. Okay, now if we look at it this, we can calculate. So how do you think we should calculate the value of like work in W1 and W2? So let me clarify one thing, that it is mentioned that the system is reversible. Okay, so for reversible system we know that efficiency is equal to 1 minus T2 by T1 here. So T2 is equal to 1 minus T2 by T1, and it can be written as 1 minus T2 is 303 divided by 1073. Okay, so this value we can we calculate it as equal to 0.7175. Okay, let me do it once more. 1 minus 303 upon 1073 is equal to 0.7175. Okay, now we can also write efficiency is equal to efficiency of engine is equal to work done supplied W1 by Q1, and since we know the value of Q1 is equal to 1900 kilojoule, we can calculate W1 is equal to 1363.3 kilojoule. Okay, since we have value of W1 and we know W net, so we can say from here W1 is equal to W2 plus W net, so we can calculate W2 is equal to 1073.3 kilojoule. Okay, so if we use this value here, so using this value we can also move forward. Let's calculate the COP for refrigerator. Okay, COP for refrigerator, since it is mentioned that it is reversible refrigerator, so we can directly use TL upon TH minus TL. So here TL is 258 Kelvin. Okay, and let's say this is the reducing amount of Q3, which is delivered here as Q4. Okay, so we can write it as 258 divided by 303 minus 258. Okay, and this can be calculated as 5.733. Okay, so we can also use like COP of refrigerator we know is equal to desired effect, that will be Q3. Okay, divided by input is W2, and from here we can calculate Q3 is equal to, so COPR into W2 we have already calculated it here, so we will get Q3 is equal to 6154.5 kilojoule. Okay, so this is our part A, which has been asked here, the cooling effect. Okay, so we calculated it as 615.5 kilojoule. Okay, part A. Okay, now we can start solving part B. It is asked that total heat transfer to 30 degrees Celsius reservoir. Okay, so to calculate the total heat transfer to this reservoir, we can let this be Q2. Okay, and this be Q4. So total heat received will be, for B option we have to calculate second part we have to calculate Q2 plus Q4. Okay, we know that Q2 is equal to Q1 minus W1. Okay, and for Q4 we know that it is equal to Q3 plus W2. Okay, so we know all the values of we know Q1 is equal to 1900, W1 is equal to 1363.3, and we also know that this our value of Q3 is equal to 6154.5, which we have already calculated, and value of W is equal to 1073.3, which I have mentioned here. Okay, so we can substitute all the values here, and on solving this we will get our value to be 7764 0.5 kilojoule. Okay, so we have completed this question number 16 here. Okay, now we will be moving to question number 17. So it is mentioned that figure showing undergoing a reversible cycle. A reversible cycle is exchanging heat with 3 thermal reservoir and develops 100 kilojoule of work. Okay, find the magnitude and direction of QB and QC. Okay, so first of all, in such questions, what we have to apply, we have to use closest inequality. So it is mentioned that this is a reversible system, so we can say that del Q by T is equal to 0. So we will apply it here. So let's say that this 5000 kilojoule is, since it is rejected from the surface from the system, so we can write it as minus 5000 by 1000. Now let's say that assume the direction of QB to be this and QC to be this. Okay, so let's assume that both heats are rejected from the heat engine. Okay, so we will proceed it as plus QB upon 300 plus QC upon 500 equal to 0. Okay, now one more thing we can do here, like since we have given work, so work done can be assumed to be like, let's say this is Q1, okay, or QA. Okay, we can write it as QA minus QB plus QC. Okay, so this work we have been given the value of 1000 and QA is equal to 5000 minus QB plus QC is okay, so we get QB plus QC is equal to 4000. Okay, from here we can find all the values. Let's say QB by 300 plus let's say that we have substituted the value of QC from here to here. Okay, you can substitute the value here, so we get it is 4000 minus QC by 500 is equal to 5. Okay, so on solving further, we can get it as, we can take QB common and we can write it as 1 by 300 minus 1 by 500 is equal to 5, minus we can solve 4000 by 500 which will be equal to 8. Okay, now solving this we will get, let me solve it first. Okay, this is 300 inverse minus 500 reciprocal. Okay, this inverse into 3. Okay, so we get QB is equal to minus 2250 kilojoule. Okay, and from this we can also calculate QC is equal to QB minus, we get it as 6250 kilojoule. Okay, now we have gotten both values. So QC is, the sign convention is correct. For QB the sign convention should be reversed. Okay, so you can say that this QB is of value of 2250 is received by the system. Okay, and this QC is rejected from the system and QC value is 6250. Okay, next we will be moving to next question. So okay, so this question it is mentioned that it is proposed that a solar energy to be used in a large collector plate, heat a large collector plate, the energy in turns to be transferred as a heat to a fluid within a heat engine. The engine would reject heat as a heat to the reject energy as a heat to the atmosphere. Experiment indicate that 0.5 kilowatt per meter square of energy can be collected at the operating temperature of the plate, and maximum efficiency of the engine is 0.2. What would be the minimum collector area that would be required for the plant to produce 1 kilowatt of used power? Okay, so from here we can see that energy is supplied, heat is supplied with the help of our solar collector plates. Okay, collector plates, and it is given that zero point 0.5 kilowatt per meter square of energies can be collected with the help of collector plates. So we can write QS is equal to zero point 0.5 into, let's say, the A with the area of the area required of the collector plate. Okay, so 0.5 into A kilowatt will be the heat supplied, and it is mentioned here that the maximum efficiency of the engine is zero point 0.2, and it is also given that work done, that is minimum, the power plant produces 1 kilowatt of fused power, so work is equal to 1 kilowatt. So we can directly apply heat efficiency is equal to work done upon heat supplied. From here we get efficiency is equal to 0.2 is equal to work done, that is 1 upon heat supplied is 0.5 into A. From here we can get A is equal to 2 upon 0.2 is equal to 10 meter square. Okay, so this 10 meter square of collector area is required to collect the power minimum required to meet with the required power of 1 kilowatt. Okay, now moving next question. Let's say this is our next question, so we will start this question now. It is mentioned that the heat engine receives half of its heat supply at 1000 Kelvin and half at 500 Kelvin, while directing heat sink to 300 Kelvin, the maximum thermal efficiency of the heat engine. Okay, so it is mentioned that there is a heat engine here. Okay, and this heat engine receives heat from two sources. Okay, and from one source is at 1000 Kelvin, another source is at 500 Kelvin, and from both it takes Q by 2, and here it also takes Q by 2, half heat. Okay, heat supplied half at 500 Kelvin, and it rejects that reject the heat at 300 Kelvin. Okay, and it produces some power, let's say produces the work done. So it is asked that what is the maximum thermal efficiency of the heat engine. So to calculate the maximum thermal, we can say that the total amount of heat which will be rejected here can be written as Q minus W. Okay, now for reversible, it is asked that maximum thermal efficiency. Okay, so maximum thermal efficiency is possible in case of reversible. So for reversible, we know that our closest inequality is equal to 0. Okay, so we will apply the same thing here. So minus Q by 2 into 1000. Okay, minus Q by 2 into, sorry, here it is temperature is 500. Okay, 500 plus we have an rejecting heat of minus Q by W at 300 Kelvin, so this will be equal to 0. Okay, now from here we can like solve Q minus, or we can like transfer the value of W is equal to on that side. So from here we get Q times of one by 300 minus 1 by 2000 minus 1 by 1000 is equal to W by 300. Okay, so on solving these values, 300 inverse minus 2000 inverse minus 1000 inverse, okay, sorry, we get the value of this to be 0.001833 Q is equal to W upon 300. And we also know that efficiency of an system is a desired effect upon heat supplied. Heat supplied is Q by 2 plus Q by 2, so it is W upon Q. And From this equation only we can calculate W upon Q is equal to 0.001833 into 300. Okay, so multiplied this value by 300, we get our efficiency to be 0.55 or 55%, or 55%. Okay, so I hope you understood this question well. Next we will be moving to our question. So now we will be starting this question. It is mentioned that the household refrigerator is maintained at the temperature of 2 degrees Celsius every time the door is opened. Let's first draw the diagram for refrigeration. Okay, so this is our refrigeration diagram. Okay, so it is said that the temperature is maintained at 2 degrees Celsius. So our, let's say, TL is equal to 2 degrees Celsius will be 275 Kelvin. Okay, and it is said that whenever the warm material is placed, the door is opened, warm material is placed inside, introducing an average of 420 kilojoule. Okay, so it should reject a heat of 420 kilojoule whenever door is opened or a new material is placed. So 420 kilojoule should be absorbed continuously from the system to maintain it at 2 degrees Celsius. Okay, but making only a small change in the temperature of the refrigerator, door is opened 20 times a day. Okay, so every day we open 20 times a day, so total heat rejected will be, so let's say this to be Q, let's say this to be Q2. Okay, or QL. Okay, so this is QL. So value of QL is equal to, or we can directly, let me give me a moment. Okay, so this heat is QL, and let's say this heat will be transferred to a high temperature energy reservoir, and it will, the system will observe some work. Okay, now it is mentioned that but making only just 20 times a day, the refrigerator operates at 15% of ideal COP. Okay, so COP actual is equal to 15%, that is 1.15 times of COP ideal. Okay, ideal, or we can also say Carnot. Okay, now it is mentioned that cost of electricity is 2.5 rupees per kilowatt hour. The monthly bill of refrigerator, what should be? Okay, next it is mentioned that atmospheric is 30 degrees Celsius. So this high temperature should be at reservoir at, that is that will be atmosphere will be 30 degrees Celsius, and which will be equal to 303 Kelvin. Okay, now it is given that total Q load, okay, QL lower, so the load on the refrigerator will be 420 kilojoule every time the refrigerator opened or the new thing or something is placed inside, but this is done 20 times a day, 20 times per day. Okay, so in a day we can see that QL QL is equal to, on multiplying this we will get 8400 kilojoule of heat will be need to be rejected on the daily basis. Okay, now it is said that the now we can use this formula to calculate the actual COP. So COP actual is equal to 0.15 times of COP ideal will be TL upon TH since this is refrigerator, this will be TL upon TH minus TL, and on substituting values we will get 0.15 into TL is our 275 upon 303 minus 275. Okay, so from here we get our actual COP. Actual COP is equal to 1.473. Okay, so we also know that this COP can also be written as our desired effect, that is, so let me write it here. So this COP actual can also be written as our desired effect, which will be QL upon supply energy input. Okay, energy input is work done. Okay, so from here we get our work done value is equal to QL upon COP, and this is our QL value 8400. So we get 8400 divided by 1.473. So from here we will get W is equal to 5701.6 kilojoule per day. So this is the work input to the refrigerator per day. Okay, now if we so we have to calculate monthly bill. Okay, so if we calculate the work for monthly work, okay, so work done in a month time, so we can multiply it by 30 into work. This was for work day, let's say, so work day, so we will get total work done to be 171048 kilojoule. Okay, now we have to convert this value of work into kilowatt hour, as because the cost of electricity is mentioned in per kilowatt hour. Okay, so to convert it into per kilowatt hour, it is simple. So we have to just divide it by 3600. Okay, so 171048 divided by 3600, this will be the value in kilowatt hour. Okay, and we will get answer to be 47.5 kilowatt hour. Now we know that for calculation of monthly, it is as monthly bill, we know that cost of electricity is equal to rupees 2.5 per kilowatt hour. So we can calculate, multiply it by total energy consumption, 2.5 into 47.5. okay, so we will get our bill to be rupees 118.75 per month. Okay, so with this we will finish this question here. Now we will move to next question. This is our question. A reversible heat engine operates with 3 thermal reservoirs and delivers 50 kilowatt power. The engine absorbs 1000 kilojoule from a reservoir at 600 Kelvin. Okay, and the temperature of the other reservoir is 400 and 300 Kelvin. Find the thermal efficiency of the reservoir. So we can start by drawing a diagram for this engine. Okay, so let's say that the thermal reservoir at 600 Kelvin provides heat at 1000 kilowatt, okay, to the engine, and this engine further interacts with operate with 3 thermal reservoir and deliver. Okay, and these both two of reservoirs are at 400 Kelvin and 300 Kelvin, and the work produced will be equal to 50 kilowatt. Okay, now the temperature, find the thermal efficiency of the engine. So we have to calculate efficiency of the engine. Okay, so for efficiency, let's say the system is let's say this heat is Q1, and let's say it is reacting heat Q2 at 400 and Q3 as 300. Okay, so from energy balance we can write Q1 is equal to W plus Q2 plus Q3. Okay, but we know that so from here we can calculate Q2 plus Q3 is equal to Q1 minus W. From we can also write Q2 plus Q3, and now Q1 value is 1000 and Q2 value, W value is 50. We can write it as 950 kilowatt. Okay, so we know the value of Q2 plus Q3 is equal to 950 kilowatt. Okay, now if we apply the law of entropy, second law of thermodynamics, and that is entropy balance. So for reversible engine we know that our del Q by T is equal to 0. Okay, so we'll apply this here. So we get minus 1000 kilowatt upon 6 at 600 Kelvin plus Q2 at 400 plus Q3 at 300. Okay, and this total will be equal to 0. So from here we get Q2 by 400 plus now Q3 we can write it as 950 minus Q2, 950 minus Q2 by 300 is equal to 10 by 6, that will be 5 by 3. Okay, 5 by 3. Okay, now so from this we can calculate from here value of Q2 hour. What will be the value of Q2? Okay, so to calculate Q2 value we can write it as Q2 times of 1 by 400 minus 1 by 300 is equal to 5 by 3 minus 95 by 30. From here we get our value of Q2 is equal to 1800 kilojoule. Okay, now using this Q2 is equal to 1800, we can calculate Q3 is equal to 950 minus Q2, 950 minus Q2, so we can get Q3 is equal to minus 850 kilowatt. So what does this minus 850 kilowatt means? It means that our assumed direction this is incorrect, and heat will be following this direction. Okay, so it means that these Q1 and Q3 both will be acting as source, and our Q2 is the sink will be acting as a sink heat. Okay, now to calculate the efficiency, we know that efficiency desired effect upon supplied heat supplied. So desired effect is 50 kilowatt upon heat supplied is 1000 from Q1 plus 850 from Q3. Okay, so we have to solve 50 divided by 1850. Okay, we will get value is equal to 0.027. Okay, so this will be equal to 2.7%. Okay, so I hope you understand this question well. Okay, so you should remember that if there are more than two you have more than two thermal reservoirs, and your temperature is unknown, or like more than if there are two unknowns. Okay, like in this case there are two unknowns. Okay, or either let's say that this heat is provided and the W is not provided also. So in case of question like this, where there are multiple reservoirs and there are at least two or more than two unknowns, then you should must apply the principle of entropy, or you can say closest inequality. Okay, and along with these you can also like use this, like here there are two unknowns, so I require at the minimum of two variables, sorry, two equations. So for that I have used energy balance equation and or closest equation. So if say let's say there are three you have three unknowns, so you should like apply three equations. Okay, so these are two equations, and according to question you can also find a third equation if such condition arises. Okay, now we will be moving to next question. So up until the last question we have already completed the questions on second law of thermodynamics. From here our questions on entropy will start. Okay, and they, of course there are few questions from entropy in last topic also, and we will start with question number 1. A process A is irreversible and adiabatic. Process B is reversible and adiabatic. The entropy change in process A and process B respectively are. So we know that since it is mentioned like this, for let's say talk about process A, which is irreversible and adiabatic, and process B is reversible and adiabatic. So like we have to calculate the what will the entropy change in entropy. Okay, so we know that ds in a process can be written as ds generation plus dq by or del q by t. Okay, and since here it is mentioned that both processes are adiabatic, so we can directly like put this equal to 0. Okay, so this ds will be totally dependent on s generation. Okay, so in case of reversible, that is ds for b will be equal to 0 because there is no entropy generation in case of reversible. But we talk about irreversible, so ds in a it should be greater than 0. Okay, because there is always a positive generation, entropy generation in case of irreversible processes. Okay, so it should be positive and 0. Option D is correct. Okay, now we're moving to next question. Question number 2. At constant temperature, a pressure at constant temperature, pressure of an incompressible fluid is changed from 400 kilopascal to 4 megapascal. Which of the following set of thermodynamic properties remain unchanged during the process? Okay, so it is said that temperature is equal to constant. Okay, and pressure of an incompressible fluid, pressure P1 is equal to 400 kilopascal to pressure P2 is equal to 4 megapascal. Okay, find the following set of thermodynamic properties remain unchanged. Okay, so we have given properties U. Okay, let's talk about properties. Okay, let's give me a moment. So we are talking about properties. So there are a few properties given. First property is given specific internal energy, second is specific volume, third is specific enthalpy, and fourth is specific entropy. Okay, so let's see. If we consider so in this question we can say that there are some conditions mentioned, that is constant temperature, which I have already mentioned. The second is incompressible fluid. Okay, so here it is mentioned for as for u. So for u is a function of temperature. Okay, u is a function of temperature only. Or if even if we don't write it like this, we can write it as like mcv dt. Okay, so since temperature is constant, this u is will be same. Okay, now if we talk about v, it is given as incompressible. So it is specific volume will also be same. Next, if we talk about enthalpy is given by u plus pv. So u is constant, v is constant, but p is increases, so h varies. Okay, varies. And for entropy is also function of temperature. Okay, and because it is for incompressible process, we can write like if you remember the formula for entropy change of a gas. Let's consider a gas. So we see there are two terms. First is like we can write it as Cp ln T2 by T1 minus R ln, okay, minus R ln P2 by P1. Okay, so from here you can see that since the temperature is constant, and but this entropy formula is applicable for gases. Okay, so here it is mentioned as it is incompressible fluid. For incompressible, we have studied in our last lecture the entropy change of a finite mass of fluid. Okay, finite mass. Okay, so for that we get entropy change is mc ln T2 by T1. Okay, so since temperature is constant, we get delta S is mc ln T2 by T1, and since temperature is constant, we get S is also same. So u, v and s all properties remain unchanged. Okay, u, v, s, u, v, s, option C is correct. Okay, now moving to next question. It is asked that the approximate entropy change when 10 kg of ideal gas having a specific heat at constant volume 3 5 r by 2 r is equal to 87 is taken from an initial state of 100 kilopascal and 300 Kelvin to a final state of 200 kilopascal and 500 Kelvin is. Okay, so it is mentioned that this is an ideal gas, so we can directly use formula for entropy change of ideal gas which I mentioned earlier. Okay, so we write it as mcp ln T2 by T1 minus mr ln P2 by P1. Okay, so we know, so here mass is given at 10 kg and we have again initial conditions and final conditions. Okay, now we need cv, so cv now we can use the formula cp minus cv is equal to r to calculate the value of cp, which will come out to be r plus cv is our 5 by 2 r, so we get cp is equal to 7 by 2 times of r. Okay, now we will use this here also. So delta s, let's take a mass common from both sides and we will take it here, and cp is 7 by 2 into r value is given at 287 and this value is given in joule per kg Kelvin. Okay, so ln T2 by T1, T2 is 500 divided by 300 minus r is 287 into ln P2 by P1, P2 is 200 and this P1 is 100. Okay, so when we will calculate this, so we get the value of delta S equal to 3141.9 joule per kg or joule, okay, per Kelvin. Okay, so this is the unit for entropy, joule per Kelvin or kilojoule per Kelvin. So we get the value of, the correct answer is B, 3.14 kilojoule per Kelvin. Okay, now moving to next question, question number 4. We can see here it is mentioned that consider an isentropic process undergone by an incompressible liquid. Okay, the change in temperature experiment liquid is delta T is equal to T2 minus T1, then which of the following is correct. Okay, so since the liquid is incompressible and we are telling that the process is isentropic, so for isentropic process we write ds is equal to 0. Okay, and since the process is incompressible, we can delta S is equal to 0 for asentropic, and for incompressible liquid we can write delta S is written as mc ln T2 by T1 is equal to 0. From here we get T1 is equal to T2. Okay, so our delta T value will be 0. Okay, here we can write T2 minus T1 is equal to 0. Okay, so moving to question number 5. And the question is the relation TdS is equal to du plus PdV when this is also known as TdS first equation. Okay, so, or first TdS equation. So this is both the TdS equations are valid for all the processes. Why? Because they are all are state point functions only. Okay, now moving to next question, which of the following is false? Okay, so let's see the option A. Mixture of ideal gas also behave as an ideal gas. Okay, this should be correct. Okay, so option A is true. And the enthalpy of ideal gas is a function of temperature only. Correct. Entropy of ideal gas is a temperature function only. This is false. Okay, this is false. Because we know that entropy of ideal gas is function of temperature and pressure, or temperature and volume. Okay. Next, the temperature of an ideal gas always decreases during isentropic expansion. Okay. Temperature of ideal gas always decreases during isentropic expansion. This equation is also true. We know that during isentropic expansion, the temperature of gas decreases, but if there is isentropic compression, then the temperature of ideal gas will also increase. Okay, so here option C is correct. That is option C statement is false. Okay, next, the water is cooled in the evaporator of a refrigeration system from 14 degrees Celsius to 7 degrees Celsius. The temperature of the refrigerant in the water in the evaporator remains constant at 3 degrees Celsius. The refrigerant removes heat from water at the rate of 100 kilowatt. Assuming the steady flow, negligible pressure drop, perfect insulation of the evaporator, the net entropy generation rate. Okay, so it is mentioned that let's say this is the evaporator. Let's say this is an evaporator. Okay, so it is saying that water is cooled in an evaporator of a refrigeration system from 14 degrees Celsius. So the water enters at 14 degrees Celsius. Let's say this T W1 is equal to 14 degrees Celsius. Okay, and the water exits at TW2 is equal to, let's say it is given at 7 degrees Celsius. Okay, now it is mentioned that evaporator temperature is constant. The temperature of refrigerant is constant at temperature of refrigerant is constant at, let's say this is the water. Okay, and it is also mentioned that temperature of refrigerant is constant. Okay, so temperature of refrigerant, let's say temperature of refrigerant is equal to 3 degrees Celsius. Now it is mentioned that the refrigerant removes heat from the water. Okay, so this refrigerant absorbs heat at the rate of Q is equal to 100 kilowatt. Okay, now assuming steady flow, negligible perfect pressure drop, perfect insulation of the evaporator, the net entropy generation in kilowatt. Okay, so if we are talking about the entropy generation, so entropy generation can be, so net entropy generation, delta S net, can be written in like two formulas, in two parts: delta S of refrigerant plus delta S of water. Okay, so the refrigerant receives 100 kilowatt of heat, 100 kilowatt of heat at a temperature of 3 degrees centigrade, that is 276 Kelvin. Okay, 276 Kelvin. Okay, now this water, this rejects the heat. I mean, this rejects the heat. How much heat it rejects? 100 kilowatt. Uh, okay, but for water we know that delta S for water is represented by MC ln T2 by T1 for finite mass. Okay, so this delta S water can be written as MC ln of T2. T2 is 70 degrees Celsius, will be equal to 280 Kelvin divided by 14 degrees Celsius, is 287 Kelvin. Okay, this, but we know that the heat removed from water is equal to MC delta T, and which can be further written as Q is given at 100 is equal to MC into delta T is 14 minus 7. Okay, so we get MC is equal to 100 by 7. Okay, so on substituting these values, let me calculate the answer. 280 divided 280 divided by 287 ln into MC divided by 7. And this term here should be mentioned positive, okay, because the negative term will automatically considered here. Okay, now if we add value of 100 divided 276, and the value of point 0.009567 kilojoule per Kelvin. Okay, now the options are given in watt per Kelvin. Sorry, it's be kilowatt. Okay, because all terms are in kilowatt. Kilowatt per Kelvin, so we get the value of 9.55. We can write. Okay, option A is correct. Okay, next, moving to next question. Question number 8. The liquid of mass m and temperature T1 is mixed with equal amount of same liquid at temperature T2. The specific heat of liquid is C. The total entropy change during the mixing processes. So we had already seen this whole derivation in the mixing of fluid. Okay, so delta is for n bodies are in contact, n mc ln am upon gm. Okay, since there are two bodies, 2 times of mc ln t1 plus t2 by 2 times of root of t1 t2. Okay, so we get the value of option B is the correct option. Okay, now if we continue to question number 9. So let's stop it this lecture till here, and further questions we will discuss in our next Q&A session. Okay, after we discuss the available energy, so after that we will start discussing the our next question session 5. Okay, thank you for this.